Good morning, Year 11. Emergency stream here because Teams is so laggy I couldn't show you what I wanted to show you. Anyways, this is a motor effect in action. Here I've got two magnets that, oops, again you can see them attract. So they're attracting across there with a magnetic field. Okay, I've also got power supply. Set that to 10 volts there. I can set it a bit less actually. And here's a wire which is just connected straight into the power supply. And you will notice that when I switch the power on, a current will flow through the wire and oops, it jumps up. Okay, there you go. That's an example of the motor effect. What we're in fact doing is we're creating a magnetic field in the wire which interacts with the magnetic field of these two magnets and causes it to move. Okay, and you can see it goes upwards. If I switch the power around, it will actually go the other way. Okay, if I hold it there, look, you'll see it wants to go down. Okay, so that is the motor effect. So there's two things that we're going to learn about the motor effect. Number one, we can actually work out the size of the force that is being exerted on the wire here, look. And that's a formula, that's quite easy. And then the other one is we can predict in which direction it will go, either up or down in the magnetic field. And that's using something called the left-hand rule, which is slightly trickier. You've got to think in 3D. Okay. So I'm just going to pause for a second. Okay, so we're back. So, whoops, pen's in the way. So this is called the motor effect. So write these notes down as I talk about them. Here you go, the motor effect. And very simply, the motor effect, let's just move this camera so I don't bump the pen. Bump the pen. The motor effect is, it describes how electrical energy can be transferred to kinetic energy, discovered by, amongst other people, Michael Faraday, one of my heroes. Okay, so that's what the motor effect actually is. Now then, let's draw a 3D picture. So draw this as we go along. Let's imagine I've got a magnet there, and I've got a magnet here. I'm drawing it 3D. The arrangement I just did, just showed you a moment ago. And let's say the magnet here, this side here is a north pole, and this side over here is the south pole. Now that means that there is a magnetic field going across that gap, a magnetic field, okay, going from north to south. If we put a conductor through it, that bit of wire, which is a conductor, and we put an electric current through it, we will get some movement. Let's just get this diagram correct. If the current was going this direction, I know that you will feel a force F going upwards like that. So we've got a current, we've got a force on the conductor, and we also have a magnetic field. Okay, now all of these are factors in affect the movement. I'm muttering now. Okay, so let's just do this. There is a formula which is called F equals Bill, B-I lowercase l. We can use a capital L sometimes. And where that is the force felt by the conductor, this is the magnetic field. Magnetic field flux density, how strong the field is measured in Teslas. That's current measured in amps, and that's the length of the conductor that is in the field. Okay, so that's just the length in meters. Okay, and that's obviously a force measured in newtons. So that's fairly simple. If we put more current through the wire, you can see that the force gets bigger. If we have a stronger magnetic field, this B field, if it's stronger magnets, we'll get a bigger force. If there's more conductor in between in the magnetic field, we will get a bigger force. Okay. Now the important thing is that we're only interested in the electric current flowing at right angles to the field. Oops. The field. Okay. Now then, let's have a think. Let's take a pause there because you're going to practice using this equation, and there is a worksheet which I'll direct you to in the lesson. So take a pause there, just applying this formula, and there are, excuse me, a number of questions with change of subject. So do those. So pause the video now, go back into the live lesson, or pick up the document will be in the chat function. Mark it, and then come back into the second part of the lesson here. Okay, so you should have paused, you should have done the calculations. Now this is the second part, which is Fleming's left-hand rule. Okay, Fleming's left-hand rule predicts which way the conductor will move, either up or down when it's in the field. Okay, and this is because of vectors and current. So if you could imagine a 3 X, Y, and Z axes, these are all at right angles to each other, okay? Where that represents the force, the direction that something will move. That represents the magnetic field, that's at right angles to that force. And the current is at right angles to the field, okay? So that tells me the field is going in this direction and the current is going in this direction, then the force is going in that direction upwards. And we can do that with our fingers. So let's do it back, where our thumb represents the force, this represents the field, and this represents the current. So let me show you. Zoom out. Look at this one here. The field is going from left to right. That's my finger. The current is coming out towards us in this direction. That's the current. And so therefore, the force is upwards. That's the force button. Okay. The field's going that way. Zoom right out this so you can see. So the field is going in that direction. The current is coming out towards us, and the force therefore is upwards. For this one, let's do this second one. Once again, the force field is going that way. This time the current is going into the paper. So I have to turn upside down. That's my field, current, and so therefore the force is downwards. Okay, it's because if you look, when you do this, this finger's at right angles to this finger, they're both at right angles to the thumb. Okay, so that's why that works. Okay, so in solving these problems, you may be given a field with a direction, you may be given the current direction. You have to work out which way the force is going to go. You have to use the Fleming's left-hand rule. Okay, so there are some second questions for you to answer. Okay, and they will be posted in chat as well. Gosh, really hard doing this online. Okay, so enjoy.